Welcome to the Ada Lovelace Day podcast. I'm Sue Charman-Anderson, and this is the delayed episode 20 from December. This month, Dr. Carola Schönlieb explains how she uses maths to improve the analysis of X-ray images. And we're talking to Hilary Harper-Abernethy about the incredibly influential astronomer Caroline Herschel. We're also taking a look at the invention of the Laserphaco Probe, a device for treating cataracts that was invented by Dr. Patricia Bath. This month I'd like to welcome to the podcast Dr. Carola Schönlieb, who is a reader in Applied and Computational Analysis at the University of Cambridge. Hi Carola.
Hi Sue.
So Carola, you're an applied mathematician. What is it that you apply mathematics to?
So I work on developing mathematical methods for imaging, which encapsulates all the way from image analysis methods like segmentation of images to processing of images such as denoising to reconstructing images from indirect measurements as they appear in biomedical imaging such as tomography or things like that. I work all the way from coming up with mathematical formalizations with mathematical models to solve certain imaging tasks, to the analysis of these models in terms of are they actually, are they solvable? Are they giving us the type of solutions that we want? To the numerical solution of those, so the implementation of these methods on the computer. The images that I'm looking at come from biomedical imaging, from various scales of imaging, from imaging, looking at whole body magnetic resonance tomography scans to molecular level of imaging cells with microscopy, go to remote sensing. I have collaborations with people in forest conservation where we look at airborne imaging data of forests, go to arts and humanities, archaeology as well, where we look at digital restoration of paintings and manuscripts and things like that. So that's my bread and butter.
That's a really exciting range of applications. Can you kind of talk me through one of them? Give me an example of the kind of work that you do.
One image processing task which appears all over the place has to do with the fact that most of the images that we are looking at or the imaging data that we are starting with contains noise. And in order to analyze, to make quantifications based on imaging data, to interpret images in a better way, or just to have a visually pleasing image to look at, one task is to remove the noise from images. And so this is an extremely basic image analysis processing task. It's, as I said, all over the place, but it's also one of the most difficult ones. And the reason is that you need to find a mathematical formalism that can differentiate what is the noise in the image and what is really the content that you want to preserve. So denoising is difficult. One of the very, quite broad and standard approaches to do this is, for instance, Gaussian filtering, is a filtering technique which basically says the noise in the image is the random, highly oscillatory component. When we think about that in frequency space, it lives in the frequency space in the very high frequencies. So one way to filter out the noise is to get rid of these high frequencies. And so this was basically what Gaussian filtering is doing. If you have encountered the heat equation before, the heat equation is an equation which diffuses an initial, let's say, heat distribution, which in our case is not a heat distribution, but is a distribution of intensity values in the image. It diffuses those, and this diffusion you can again think as an averaging process. And this averaging process is again, you can think of that as getting rid of high frequencies. If you have high frequencies, high oscillations, if you're averaging them, it means that you're making out of these high frequencies, you're approximating them with a low frequency. And so that is a very common approach because it's extremely simple. One of the issues is how much do you average, which has to do, if you think of Gaussian filtering perspective, with the width of the filter that you're convolving your image with. has to do with, when you think of the heat equation, how long you are solving the heat equation for. The heat equation is an evolution equation. So depending on when you start with your initial heat distribution or your intensity distribution of the gray values in the image, how long are you doing this averaging process? How often do you iterate this averaging process? So when do you stop? This is one issue. So when do you decide you have, there is no more noise in the image? And the other issue is this is a filtering technique that is killing all the high oscillations. And high oscillations are sometimes not just noise, but if you think about boundaries of objects, so the regions in the image where the object interfaces background, this is where my intensity function, the gray values, are jumping significantly. So they might jump from white, which let's say this is 255 as an intensity value, to 0, which is black. Let's say you just have a black and white image. And so that is also a highly oscillatory component. That is also why these very simple techniques, they are not just killing the noise, but they're also blurring out edges of objects, these interfaces between objects and background. And that is something we don't really want. And so one of the things that a lot of mathematical effort, and in particular also my effort, went into is to develop similar, kind of motivated by this heat equation, similar type of mathematical techniques based on partial differential equations, which are, the heat equation is one example of, but that are more nonlinear, that take into account the structure that you have in the image, which means, for instance, that you would diffuse still to kill a highly oscillatory component, but you wouldn't diffuse everywhere in the same way. So your averaging process takes into account if there are significant changes in the image, like edges. You wouldn't average as much as if you would be in areas where nothing much is happening, where your intensity function doesn't change a lot, and this highly oscillatory component is the only thing that changes.
I'm kind of used to processing photographs on my computer, and I have to admit, it had never occurred to me that maths was involved. You just click a button and it happens. So how hard is it? Because for humans, it's incredibly easy for us to look at a photograph and say, well, this is the foreground and that's the background and here are some edges. How hard is it to get a computer to do that? And why is that important?
Yeah. So I actually sympathize. When you visually look at an image, it's very easy for us to understand what is going on, to decide this is an object, this is a human, and this is the background, this is grass or a sky or whatever it is. So it's very easy for us to understand that, but that also tells you how complex we as a human can perceive the world, how complex this process is. And to do this in an automated fashion, which is what you want to do when you are developing mathematical methods which can, you just write down an equation or a formula that should do it. It's very hard to do this with a simple mathematical model. And so when you think about edges, and again going back to the intensity function, as I said, edges in an image are places where the intensity function is changing significantly. And so when you think about that and you think about change of a function, you think about, okay, so this brings you to the notion of derivative of a function. So maybe these are places where the derivative of this image function is very large. This is one of the ways to do edge detection, is to look for the places in the image where the derivative of this image function is very large, and to say where it's large, this is where there is an edge, and where it's small, this is where where we are inside an object or where we are in the background or something like that. And so that is one of the driving factors, or one of the main principles that is used in image segmentation, and one type of image segmentation. Why is it hard? Because we are in the real world, things are not perfect. If, for instance, the contrast in your image, if there is a lack of contrast in your image, it also means that this significance that the derivative is large versus it's not large might be not so significant. So this difference between large and not large. Also noise, we talked about noise before. Noise can also irritate this process, because high oscillations would also have large derivatives. So you somehow have to smooth this out before you want to detect the really significant edges in the image as the ones with large derivatives. And so this is really extremely hard to find this systematically if you want that to be applicable to a wide range of images. And then, there are different techniques to do segmentation. Edges are one, but sometimes if you want to segment an object in an image, it might not have a very clear edge. And so other things come in, segmentation in terms of texture. Maybe there is a different texture inside of the image than outside. Segmentation just based on average color. Maybe the average color inside the object is different to outside. Different types of machine learning techniques where you are saying, well, there are not always clear edges between object and background, and there is not always an average color that I know of, which is the one inside and outside. But maybe I can look at enough examples of where I know what the segmentation should be and learn from these examples. So instead of coming up with a handcrafted model like the one where I'm looking for large derivatives, I'm just saying I'm starting with a kind of black box approach, a machine learning approach, and I'm learning how to segment from looking at enough examples.
So you mentioned earlier about medical imaging. How do you apply this kind of work and mathematics to medical imaging?
One big component in medical imaging is that a lot of the images that clinicians are looking at, that radiologists are looking at and so on, they are not images originally. So when they come out of a computer tomograph or of a magnetic resonance tomograph, this machine is not giving you an image directly. So this is what I mentioned at the very beginning. One of the things we are working on is to reconstruct images from indirect measurements. And this tomography examples are typical instances of such indirect measurements that you're starting out with. So to just give you an example, in X-ray, for instance, or what a computer tomograph, let's say, is measuring is it sends X-rays through your body. So you somehow want to visualize what is inside of your body. So what it's doing is it's sending X-rays. The X-ray is entering your body, let's say, from one side. It's exiting from the other side. Let's assume everything is perfect and this is just a line that it's traveling along. And so on the other end, where the X-ray comes out again, there is a detector which measures the energy this X-ray still has. So you know what the energy of the X-ray is when you send it out, and then you measure the energy when it comes out at the other end. When the X-ray is traveling through your body, depending on which type of materials it hits, bone, tissue, air, whatever, it experiences different levels of attenuation depending on the type of material. Bone is, for instance, more attenuating than air, of course, or tissue, which is like a watery structure, let's say. And so what you're really measuring at the other end is the energy attenuation that this X-ray has gone through your body. And you can formulate in mathematical terms, in terms of an integral over the energy attenuation along the line that the X-ray took through your body. And so these line integrals are also called if you now assume that you have sent X-rays through the body from all different directions that you can think of in three-dimensional space, you get a different parametrization of the different densities of bone and tissues and different materials inside of your body. And this parametrization is called the radon transform of a function. So the function that you're interested in is the different, bone and tissue and so on that you want to visualize inside the body. But what you're measuring are line integrals of this density. And so one extremely, challenging and difficult problem is and where you can see that mathematics is how to go from these measurements, from these tomography measurements, back to an image, back to the function itself, the intensity function that should visualize your bones. And so all of this, again, is complicated because there is a mathematical theory which tells you, which asks the question, can you reconstruct a function from its line integrals? And this goes back to an Austrian mathematician called Radon, long before actually the invention of computer tomography, which is another fascinating topic I'm not going into. But you can see that, pure mathematics actually, which was in this case very pure mathematical question, had a huge impact later. but it's complicated by the fact, again, that things are not perfect. You're not collecting X-rays from all, different angles that you could think of. You have a limited number of angles that are being collected. You don't actually want to collect X-rays from so many different angles because you don't want to radiate the patient too much. And then there is noise. There is always noise. So all of this gets more complicated. And this is one example in biomedical imaging where mathematics is really at the core, to go from the measurements to something that the clinician can actually look at.
There's quite a broad range of applications for this kind of image processing. And I know you've done some work with pied flycatchers. Can you tell me a little bit about that?
So this was a segmentation problem. So it's a collaboration that we started with a zoologist in Cambridge who came to us with a database of photographs. And these photographs showed pied flycatcher birds, she holding her hand holding the pied flycatcher bird, some kind of measurement device like a ruler that she also held in the same hand, and then her taking the picture with the other hand. So lots of pictures like this. She came to us with the hypothesis that the male birds of this species, they have a white blaze on their forehead. She said that there is a hypothesis in the community, in her community, that the size of this blaze relates with or correlates in a way with the amount of reproduction. So if you want, with their sexual attractiveness or something like that, or how much do they reproduce? So she said there is no real good way at the moment that people are using in order to quantify this, how to actually measure the size of this blaze. You have the photograph, you have the blaze, you have a measurement device in this photograph. So how do you go and make out of this a size in terms of square centimeters or something like this that this blaze has? And so what we did was we developed kind of image analysis pipeline, which first of all segmented automatically the blaze on the forehead of these flycatcher birds. And again, this was challenging. It was not just an edge detection approach which worked, because this blaze, the bird has feathers, and these feathers are kind of fractal. So there's a lot of texture, and so the boundary of these blazes was also very oscillatory and very fractal. So there wasn't a clear edge that you could detect. So we really had to do something else, which was based on different texture and color features that we used in order to detect and segment this blaze. And then as a second step, we had to, once we segmented the blaze, we could count the amount of pixels that were inside of this blaze, but then we had to relate this to a physical size. And for that, we used the ruler, and we detected the scale on the ruler and used that to say so and so many pixels are 1 millimeter or something like that. And and so, unfortunately, the result was that the hypothesis is probably not true. So it was a kind of negative answer. But it was an extremely exciting project. And in fact, what is for me even more exciting is that a very similar type of segmentation technique we used in an extremely different application, which was in this forest conservation collaboration that I have, which I mentioned at the beginning, to, in this case, not segment blazes, but to segment trees and trees from airborne imaging data.
It's kind of amazing to me that you're using similar techniques across sort of just denoising and medical imaging and bird conservation and forest conservation. And I had never really considered the impact that maths could have in these kinds of areas. How did you end up working on these sorts of problems?
Yeah, so that's an interesting one, because when I started my PhD, I initially didn't work on image processing. So I started out working on partial differential equations, where, I gave you this example of a partial differential equation, which was the heat equation, but I worked on another partial differential equation, which is called the Cahn-Hilliard equation. This was my first, scientific paper that I've written, my first project that I worked on in my PhD, is to look at this Cahn-Hilliard equation. And this Cahn-Hilliard equation, again, has nothing to do from the outset with image processing, but it was actually proposed by Cahn and Hilliard to model the phase separation and coarsening of binary alloys. So what I mean by that is, think about two different types of materials, let's say two different types of metals. When you heat them up to a certain temperature, they mix, and then you kind of cool them down and they start separating. And this equation is a model for this separation process between these different, let's say, metals, between these two alloys, and also subsequently, so they start separating, and then they start this coarsening process, which is that smaller regions of the same metal kind of merge together and build larger regions. So this Cahn-Hilliard equation is really this type of model, and my first paper was on a particular mathematical theory related to this equation that had to do with the stability of solutions of this equation. And at the same time, a colleague of mine from Los Angeles, from UCLA, published a paper where she used this same equation, the Cahn-Hilliard equation, for image inpainting, where image inpainting is basically an interpolation task. Think of you have an image, and part of this image is damaged. So you have an area where all the image intensity information got lost. And so what you want to do is, based on the intact part of the image, you want to restore what has been lost in this damaged region. So restoration is one example. The other one, and that's exactly the same, abstract task, is when you want to create special effects. You have an image and you select an object that you want to remove from this image. Then this object that you want to remove takes on the role of the damaged area that I talked about before, and you want to replace this object again by something that is suggested from the rest of the image. So it's a kind of interpolation. You interpolate, if you want, you interpolate color values around this area. Either it's the damaged area or this object you want to remove, you interpolate it in order to remove it, to remove this object, for instance. And so she used the Cahn-Hilliard equation to do this. Yeah, and that was really fascinating for me. And that's when I got started on image analysis and image processing, and I never stopped ever since. So,
and it seems to me as well, because there's this sort of stereotype in maths of, it's a terribly lonely profession and it's you and a whiteboard. But it sounds like your work really requires a lot of collaboration with people from a wide range of different disciplines. Is that the case?
Yes, so it's absolutely so. To collaborate with other, both with other mathematicians, but also with researchers from other disciplines, is really essential in mathematical imaging. To collaborate with other type of mathematicians is essential because different mathematical areas are important to solve these imaging tasks. So I talked about, that we need modeling. We need to come up with a mathematical model. We need to analyze this, and then we need to numerically solve this. So lots of different aspects come in when you think about noise and the randomness of noise. This is statistical. So there is statistics. There's functional analysis, there's optimization, computational analysis, there's partial differential equations, there is machine learning. So, all of this is not that one person can know very deeply everything about one of these mathematical fields. So it's essential to collaborate in order to make really big advances. And then if you want to have an impact in applications, you really have to collaborate with a person who works in this application, because you need the domain-specific knowledge in order to come up with the right model to solve this problem that they have. So it's really, and that's really the fun part, I think. I really, you still, as a mathematician or as any kind of researcher, you need also the time to sit down and think for yourself and to, write things down and you need to have this time as well. But you also, is essential these times when you spend together in front of the blackboard and you discuss and you go, I don't know, I go to our university hospital and I meet the clinicians there and they explain to me the type of images they have. They explain to me what are the lesions that they see in these CT images and why do they classify them as lesions and why not. All these things are so important. And make it exciting, I think.
So if someone's listening to this podcast and they think, this sounds like a really awesome career, what advice would you give them in terms of how do you get into this area?
Well, first of all, study mathematics. I really think I really enjoyed my undergraduate studies, my graduate studies. So study mathematics, it's very fascinating. Whatever you do, you can go in so many different directions. It opens up so many different things, So study mathematics, go in, really let yourself be, involved in this whole mathematical area. So mathematical abilities are important. What is important also is to keep being flexible. So, you're studying mathematics as an undergraduate. When I did that, I would have never thought that I'm going to end up looking at lesions in CT images. Yeah, so to be brave enough to go into different areas. I did my PhD on partial differential equations, but at some point I realized I need to, catch up on my statistics knowledge. I need to catch up on harmonic analysis or whatever, So you need to be able to be flexible and learn about different things along the way. Be open to new ideas. And I think what is also important is, as I said, collaboration is essential to develop good communication skills. Starting discussing with a mathematician from a different area, from a different mathematical area, requires some effort to start speaking the same language and to start understanding each other. And then with another discipline is, of course, even, is an even bigger step often. Yeah, so I think these are the qualities. Be brave and be passionate about what you're doing.
So what is happening for you next? What are you looking forward to?
One of the things that I'm extremely excited about at the moment, excited, fascinated, and also a bit worried sometimes, is this revolution that we are seeing at the moment with machine learning and deep neural networks and all these kind of things. So I'm very fascinated by what these deep neural networks, by what deep learning can actually do. And then, so this is on the one hand. On the other hand, I'm coming, from the story that I was telling you. You might appreciate that I'm coming from a background where I'm developing these handcrafted mathematical models. This is really what I've been doing. So I'm trying to understand what is important in images, what are the structures that we want to use to solve a particular problem, and turning those into mathematical equations. And there are advantages and disadvantages to this. And I think to both areas, the mathematical models are really exciting because they're very generalizable. We talked about pied flycatcher birds and tree segmentation, and really an extremely similar model has been used. They are rigorous, so they give you guarantees, so you know how robust they are. How robust are they when you change? When you're putting an image into this analysis pipeline, whatever this analysis pipeline is, let's say a classification task, you know that if you change your input, this image a little bit, let's say you flip one pixel or whatever, then you know also that the result, let's say in this case your classification, will be very close. So it will not be far off from the classification of this original image. So all these kind of things you know about mathematical models, but then they're limited because they're handcrafted. On the other hand, in machine learning and deep neural networks, these are highly parameterized models. You're basically starting without a model. So you just start with 1 million of parameters. And you are learning the model based on these 1 million of parameters. You're learning the model by looking at enough examples. And this is what makes these deep neural networks so extremely powerful, because they can adapt to imaging data so well. But then they don't, at the moment, it's not understood how they work. It's not understood how stable they are. In fact, there are a lot of examples where you see problems with stability. You have these adversarial errors that people are talking about and that you see a lot. And there is also a lack of generalizability, of course, because let's say your network can only deal with images that it has seen in the set of examples that you have shown to it, or at least close enough images, to this type of examples that it has learned its model from. So I think what a lot of people in the mathematics community, in this mathematical imaging community, are quite excited about at the moment is to find ways in the middle, to find ways, first of all, ways how to explain some of the things that are happening with deep neural networks, but then also how to combine those with really genuine mathematical modeling. And, sometimes we really have ideas of what the mathematical model should be. When I talked about the radon transform, it's clear that this process from image to measurements, how an image is related to the measurements that the computer tomograph is giving me, this is a physical model that we understand. So why should we throw it away? And so these kind of things, how to combine these two worlds to, in the end, the vision is to get a framework where we can take advantage, where we have only the advantages of both worlds together. That is something that I'm very passionate and very excited about at the moment.
That sounds fantastic. It's been really fascinating for me to learn more about how maths actually is applied in areas that I just would not have expected. So thank you so much, Carola, for talking to us today. I really appreciate it.
Thank you, Sue.
Thanks to Carola for explaining the important role that maths plays in image processing. You can find out more about Carola on our website at findingada.com/podcast. Our podcast is made possible thanks to the generous support of ARM, our exclusive semiconductor industry sponsor. You can find out more about ARM's energy-efficient microprocessor technology on their website at arm.com, and you can follow them on Twitter at ARM Holdings. Now it's time for our invention of the month. This month, we're looking at a machine that has improved the lives of countless people around the world. An invention that restores sight to people whose vision is impaired or even completely lost. Now, most of us have heard of cataracts. Indeed, most of us will either know someone who has had them or will experience them ourselves at some point in our lives. A cataract occurs when your eye's lens clouds over, making vision blurry at best. In the worst case, cataracts can result in blindness. Your lens is made up mostly of water and neatly arranged proteins. If those proteins start to tangle, they form clumps that prevent light from passing through, and so your vision blurs. The history of cataract surgery goes back hundreds of years, but by the 1950s, medical advances made it possible to replace a clouded lens with an artificial one. In the late 60s, the technique of phacoemulsification was developed, using ultrasound to pulverize the damaged lens, allowing it to then be sucked out of the eye and replaced. At around the same time, Dr Patricia Bath was an intern at Harlem Hospital. She finished her training at New York University, where she was the first African-American resident in ophthalmology. Bath noticed that black patients had double the rate of blindness as whites, primarily due to a lack of access to appropriate healthcare. Determined to do something about such an appalling situation, she combined public health, community medicine, and clinical ophthalmology into a new discipline, community ophthalmology. Trained volunteers visited senior centres and daycare programs, testing for cataracts, glaucoma, and other conditions that could threaten vision. In the early 80s, Bath began to work on a new device to remove cataracts. The technology she needed to realise her idea didn't exist yet, though, and it took her 5 years to complete the research and testing needed to finalise the device in 1986. Bath's Laserphaco Probe uses a laser instead of ultrasound to vaporise the lens, the remains of which are washed away as liquid flows through an irrigation line and is extracted through an aspiration tube. A replacement lens can then be inserted. Bath patented her idea in 1988, becoming the first African-American woman to receive a medical patent. The Laserphaco probe is now in use around the world to quickly and almost painlessly treat cataracts. It can also be used to treat diseased corneas, allowing them to be removed and replaced by artificial corneas in a process known as keratoprosthesis. Using this process, Bath has restored sight to several people who've been blind for over 30 years. In 1976, Bath and 3 colleagues founded the American Institute for the Prevention of Blindness, which works to ensure that everyone can access eye care, regardless of their economic circumstances. The AIPB has worked in countries around the world, in South America, Africa, Asia and Europe, as well as in the US, to promote blindness prevention and to treat eye disease. Cataracts are one of the leading causes of blindness worldwide, and about half of us can expect to experience them by the time we're 80. So if one day you end up having laser surgery for cataracts, you might want to say a little thank you to Dr. Patricia Bath. So this month I'm joined by Hilary Harper-Abernethy, who is an amateur astronomer and also interested in the history of astronomy. Hello, Hilary.
Hello, Sue.
It's great to have you on the podcast.
Thank you very much. Delighted to talk to you.
So who are you going to be telling us about this month? I'm guessing it's going to be an astronomer.
She is an astronomer. She's one of the first people to ever be paid as a scientist, and her name is Caroline Herschel. And you will probably recognise the surname because she was the sister of William Herschel, who discovered the planet Uranus. But Caroline was far, far more than just William's assistant, which has been pretty much her historical claim to fame.
Yeah, so definitely just scanning through her Wikipedia entry, there's a lot of focus on her being his assistant, but she did a lot more than just sort of organise his notes. Absolutely.
Well, for a start, she devised a system for recording the notes and greatly enhanced the records of stars. She almost had an intuitive arrangement with him in terms of his observing and her ability to then notate what he observed. She was also a passionate astronomer in her own right. When William wasn't there, and often he was away for months on end, Caroline continued with her own observation, discovering her first comet when she was alone at home. So she was very much known as a comet sweeper. She systematically scanned the heavens and recorded several comets. She's got lots of discoveries to her own credit.
It sounds like very methodical, meticulous sort of work.
It hugely is. I think both their personalities suited that sort of work, it's fair to say. And I think it was her absolute attention to detail and intense concentration. And for both of them, their ability to just kind of ignore their own comforts to focus on the job on hand that enabled them to be so prolific in their discoveries. And a lot of that was down to actually having state-of-the-art equipment. William particularly was an excellent telescope maker and lens maker. So they had the best equipment. They had dark skies in the way that we can only dream of nowadays. And they had the opportunity to do that. But that's not how they started off in life.
Oh, so how did they start?
They were born in Hanover, in what is now Germany, but Caroline was born in 1750. William was about 11 years older, and they were the children of a musician. And William grew up to follow his father's tradition and be a military musician. And he moved to England initially as an organist, a player in Bath, which was a very, very happening, fashionable town at the time. And it was his desire or need to have an assistant that enabled Caroline to eventually join him. And in many ways, William saved Caroline from a life of domestic drudgery. It was very much a kind of Cinderella rags to riches sort of story, which is why I find her so fascinating in many ways.
Because it was definitely not a common pastime for a woman in that era to be having anything to do with science.
Absolutely. And in many ways, she was absolutely the first woman to ever be paid as a scientist, one of the first people to ever be paid as a scientist. And she was also one of the first women to be awarded a Royal Society Gold Medal, alongside Mary Wollstonecraft at the same time. But fascinating lady. Caroline faced quite a bit of childhood adversity. She was born to, as I said, her father Isaac. Her mother was a kind of a social climbing, not terribly literate lady. And Caroline was everything she wouldn't want in a daughter. Caroline contracted smallpox when she was 4, so was disfigured by that. And then at the age of 10, she developed typhoid, so she never grew beyond the age of 10. So at her tallest, she was 4'3". So this tiny, quite plain lady, quite feisty, clearly intelligent but uneducated, was basically used as a domestic servant because her beloved father told her to take against all sorts of marrying, saying, as I was neither rich or handsome, it was not likely that anyone would make me an offer, till perhaps when far advanced in life, some old man might take me for my good qualities. I think she pretty much decided against marriage early on, if that was her only option. But her mother recognised that she had an industrious servant. And in fact, when William eventually brought her over to England, he had to pay his mother for a maid to take Caroline's place. So she had a bit of a rough time in Hanover, particularly after her father's death. So William was very much her saviour, and it in many ways perhaps explains her devotion to him.
Yeah, and definitely because of the issues around status and what a married woman could and couldn't do, a marriage would have very likely ended her astronomical career. She's known for her comets.
She discovered 8 comets between 1786 and 1797, which was a feat that most people would actually probably give a limb for nowadays to be able to discover those. She also embarked on a project of cross-referencing and correcting the catalogue that had been produced by John Flamsteed, who was the first astronomer royal, and it was his life's work. It took him decades, and it was published just after his death. So she added another 560 stars to that and also corrected some of his observations because of her interest and knowledge of spherical trigonometry. They were able to record things so much more accurately. And in many ways, that ended her own research. That was kind of quite an intense work until many years after William's death, and she returned to Hanover. She then started to collate a collection of nebulae for his son John, who was also an astronomer. And she completed a catalogue of 2,500 nebulae. And in 1828, she was awarded the Royal Astronomical Society Gold Medal for that piece of work, which was a hugely impressive feat and incredibly meticulous.
Yeah, it's very hard to wrap our head around how long that must have taken her, because completing a catalogue doesn't necessarily sound glamorous. And the works that went into that, certainly, I cannot imagine that was glamorous. I imagine that it was cold and hard work.
Yes, absolutely. Absolutely. But she did have a long life in which to do it. She was born in 1750, as I said. She died just 2 months short of her 98th birthday, which is a phenomenal age span for any age, but certainly for 1700s, 1800s. So she had a very, very long and busy life and was feisty almost up until the end, and kind of entertained by the King of Prussia right up to a couple of years before her death.
So her sort of final years, we normally think of people slowing down and taking up more relaxing hobbies, but she carried on with sort of looking at constellations and comets.
Absolutely, until her sight failed her, really, and she was well in her 90s at that point. Her nephew John went to visit her in Hanover, And he describes her, this was in 1832, she was 83 years old. She runs about the town with me and skips up her 2 flights of stairs. In the morning till 11 or 12, she's dull and weary, but as the day advances, she gains life and is quite fresh and funny at 10 p.m. and sings Old Rise and even dances. So I can imagine this like tiny 83-year-old lady dancing and throughout the night. Typical astronomer who tend not to sleep during the night time.
Very difficult to do astronomy if you're asleep.
Yes.
And definitely she sounds like not a morning person, which I relate to. What is it about Caroline that resonates with you? Why do you find her story so fascinating?
I think in 2 things, really. One is her immense character. She's an absolute belief in her ability to learn. She never said never, despite the fact that she had no opportunities. I contrast her with myself. We have many similarities and many differences. I'm also a singer. I've also got a brother who's an astronomer, although not the astronomer royal, but who was a huge inspiration to me. And also in music as well. He's also a musician. So I can kind of identify with her singing. But also, as I've got older, I've developed my interest in astronomy. I'm my particular interest is in moons rather than comets. That's a real passion for me. So she was really frustrated by her domestic drudgery and the limited role for women, particularly of her class. She was born into very, very modest surroundings. She certainly wasn't privileged in any way. I've got several science degrees and I take them for granted. I've never had to ask my father or my brothers or my husband whether I could or couldn't do something. I've had complete autonomy in my choice of career direction, my choice of qualification. I didn't have to struggle against kind of class stereotypes or gender stereotypes to enable me to do that. She clearly didn't suffer fools. She was very, very determined and showed great perseverance. And she had this absolute desire to be useful. So a great frustration in her latter years was that she felt her body was failing her. She still had this sharp, acute mind. And she just felt that her body was letting her down, particularly when her sight started to go. So she had this burning ambition to be independent. I think she deeply resented the lack of opportunity that she had and the control that her brothers held over her, benevolently from William's point of view, but her eldest brother originally gave her a terrible life until William rescued her. So, to the similarities, but also the contrasts make her particularly an inspiration to me. I'd love to have met her. I'd love to have been one of my dream dinner party guests.
See, it's interesting, though, that for women of her era who were interested in the natural world, there seems to have been sort of 2 ways they could go. You either did sort of botany and illustration, which was a very popular way for women to get into science, or astronomy. And astronomy has always been very welcoming, and still is very welcoming, of amateur astronomers, and you can still make valuable contributions to our scientific knowledge as an amateur astronomer now.
Absolutely. And, lots of amateurs do have access to remote telescopes. So it's not necessarily around having wonderful equipment on your own doorstep in a dark sky site. So some fabulous imaging can be done using remote telescopes. And I know certainly friends of mine are involved in that. So, and I in many ways, I envy the dark skies. One of my favourite ways of being an astronomer, because I unlike Caroline, I'm not a night owl. I'm not natural. I'm an early morning person generally. So one of my favourite ways of doing astronomy is camping or going to dark sky sites where we can see amazing stars formations without telescopes, but also amazing visions with them, away from the kind of the big city smog. That actually in the 1700s and 1800s there were good skies for astronomy. So hence most of the discoveries were made then.
What do you think has been the lasting part of her legacy?
I think in many ways, there was a huge myth surrounding Caroline as this handmaiden to William. And in many ways, she perpetuated that herself. She sometimes said, I did nothing that a well-trained puppy dog could have done. And then in many ways was very self-deprecating and played down her role in William's success. But we actually know an awful lot about her because she was a prolific diarist and letter writer. She was a wonderful correspondent. So actually reading through her correspondence and her memoirs gives a wonderfully vivid picture of both society in that 100-year stretch and also as well as scientific developments. Although she was born into very modest backgrounds, by the time she came to the end of her life, she was feted by royalty, scientific circles herself. She was, immensely respected. She had a fascinating range of friends and acquaintances who she'd write to and was very, very kind of up to date on what was going on in the world. So, and also some of the diaries were real minutiae around, kind of arguing with the butcher or whatever. But again, it gives this wonderful snapshot of a real flavour of what life was like in those days. Amazing lady.
Yeah, absolutely. And I think what's fascinating and what I think's really truly impressive is that the women's contributions were quite often claimed by men, whether that was a relative or someone else. You do have these women who were doing incredible work but just didn't get any recognition, and she did get recognition for her work, which was highly unusual.
Yeah, she was an old lady by the time she did, but yes, she very much did. Yes, and that was wonderful. I mean, her salary was £50 a year. Quite modest, but it was so precious to her to be earning her own living rather than just being kind of that. Also, the housekeeper of William's household up until the point he got married, which was quite late in life. So in many ways, she lost quite a bit of status when William married his wife Mary, and it was quite an acrimonious relationship initially. But although the women eventually became very close friends, and she was devoted to their son, but she suddenly found a huge loss of status as the head of William's household, and had to kind of work or live in, the observatory rather than as he set up home with his new wife and child.
That must have been really difficult for her, to have been really central to his life for so long and then suddenly being replaced.
I can imagine it was very difficult. I think later on she regretted perhaps some of the things she'd said about Mary, and as I said, they did become good friends, and I'm sure probably the birth of young John was the catalyst for that, although that's only an assumption. But they were very close, and she devoted to John's wife and his family, and corresponded with them all right up until her death. So, we do get a real flavour of that strong affection. Although she never returned to England, John would visit her in Hanover. And I think she probably regretted leaving. I think it was a bit of a knee-jerk reaction after William's death. Although, as I said, she was entertaining the King of Prussia well into her 90s. So she was quite feted when she was over there. She had some notoriety.
Absolutely astonishing character. And her contributions are incredibly impressive. So thank you so much for telling us about Caroline Herschel.
Well, I'd encourage anybody to read as much as they can about it because it really, really is fascinating. So thank you very much for having me talk to you.
It's been a pleasure. Thanks.
Thank you very much. Bye-bye.
Thanks to Hilary for telling us about the groundbreaking work of Caroline Herschel. You can find out more about both Hilary and Caroline on our website at findingada.com/podcast. Now for a small announcement. After 20 episodes, the time has come to put the Ada Lovelace Day podcast on hiatus. Our mission is to inspire and support girls and women in STEM, and in 2018 we have some big projects coming up that are going to demand quite a bit of our time. So a final thank you to our sponsor, ARM, for their support of this podcast over the last 20 months. And thanks also to our editor, Andrew Marks, whose help has been invaluable. You can still find us on SoundCloud, iTunes, Google Play and Stitcher, where you can delve through our archives. And you can keep up to date with what we're doing via Twitter, where we are at Finding Ada, and on our Facebook page at facebook.com/Ada Lovelace Day. So thanks for listening, and we'll see you on Twitter or Facebook.